In a previous video, we have studied how to integrate this double integral dx dy when this D is a rectangular closed region. In this video, we will extend this to non-rectangular region. Actually, it's a closed Jordan region. So how do we do that? But before dealing with general closed Jordan regions, we deal with a special type of Jordan regions. That is something like this. In xy plane, we consider two functions such as this and this, and that are defined on a closed interval. Let's say a and b. So these are in closed. This is a closed interval, and let's say this is a psi of x. So y is equal to psi of x, and this is y is equal to phi of x. And so two functions and two vertical lines. So by connecting these, we have a closed Jordan region. That is this region. Okay, so suppose D is this region, and we want to integrate some function of x and y on this region. So for more formally, this region can be written as this set. So this is a set of x and y such that x is between a and b, and y is between psi of x and phi of x. And clearly this is a Jordan region because there is no crosses here in this in the boundary. So we may define some parameterized function, one parameter function that's between 0 and 1 that goes like this. For example, from here to here to here to here. Now we are going to find a way to calculate this integral. So suppose f of x and y is some function of x and y, and D is some set defined like this for some given functions psi and phi. So how do we do that? Actually, we are going to calculate this as an iterated integral. So that would be something like this. So x varies from a to b, and y varies from each value of x. The value of y varies from psi of x to phi of x. And f of x and y, and dy, and dx. So here, we consider f of x and y as a function of y alone. So fixing the value of x, so it's a univariate function of y. And after integrating this, then we consider the resulting this integral. Let's call it f1 of x. So by fixing the value of x, this is a function of y alone. After integrating this, we consider this result as a function of x, which is a univariate function, and we integrate with respect to x from x equal to a to x equal to b. So now we are going to show that this method of iterated integral actually works. Okay, we are assuming that this f of x and y is a continuous function on the region D. Okay? And we define f1, uppercase f1 of x as this inner integral. That is, so we fix the value of x and consider f of x and y as a function of y alone, and then integrate it with respect to y. And we now show the following lemma. Okay, so f1 of x, so defined as this one, is a continuous function. Continuous on the interval between a and b. All right, let's prove this lemma. First of all, we are actually assuming that this psi and phi, they are continuous functions, okay? Okay, so first of all, to show that this function is continuous on this closed interval, we show that this function is continuous at each point in this interval. Okay, so we show that fx is continuous at arbitrary x0 in this interval. Okay, and let epsilon be any positive number, arbitrary. And since psi and phi are continuous, there exists some delta such that the difference between psi of x minus psi of x0 and the difference between phi of x and phi of x0, they are arbitrarily small. Usually we express this as for all some positive epsilon, there exists delta such that this and this are less than that epsilon. But we are going to use epsilon for other purpose. So just say this can be smaller than any positive number. Okay. Now we define two constants. That it's c, that is the maximum of phi of x and phi of x0, and d as the minimum of phi of x and phi of x0. So we are considering some region like this. So let's say this is x, this is x, and x0 here. So C is the maximum of, so this is psi, this is phi, maximum of this and this. So in this particular picture, that should be this value. So this value should be C. So and in this particular picture, the minimum of phi of x and phi of x0 is this one. So D would be this one. Okay. And using these C and D, we may assume that f1 of x minus integral between C and D of f of x and y dy is less than some arbitrary positive epsilon divided by 3. And similarly, we have x0 minus c d f xy dy less than epsilon over 3. Well, this may look a bit tricky, so let me explain a little bit. So let's consider the first one. Suppose, for example, C happens to be equal to f of phi of x0, okay? And D is equal, happens to be, wait a minute, in this case, it's x, okay. So suppose C happens to be this one, and D happens to be this one, okay? So let's consider f1 of x minus c d, this, okay? So let's say c is equal to phi of x and d is equal to phi of x0. And f1 is, by definition, is this, okay? So the lower bound of integral is psi of x, and the upper bound is phi of x. So this is equal to psi of x, phi of x. And this part, we split this integral into two parts, okay? So psi of x, phi of x. And plus phi of x and phi, since okay, so this is phi of x0, so this is phi of x0. Okay, we split this integral into two integrals. So that is, okay, so using this in, so we are integrating from here to here, okay? And integrating from C to D is integrating from here to here. So here the lower bound is phi of x, so that is actually larger than this one. So this integral should be, assuming this function is positive, then this integral should be negative. So we first integrate from here to here, then subtract this this part. Okay, so this part corresponds to this integral. Okay, now if we calculate this, this integral and this integral will cancel. So what we have left is this integral. Maybe we can swap this up and lower bound to have x and x0. But anyway, this interval here is very small, right? Because it can be made arbitrarily small, as we have stated here, as long as the distance between x and x0 is less than delta. So this can be made arbitrarily small. Okay, so that's why we have this inequality, where epsilon over 3 is an arbitrarily small positive real number. And the same applies to this one. And we have explicitly dealt with the case where this C happens to be this one, but and D happens to be this one, but you can try any other combinations and still have the same result. Okay, anyway, all of these stem from the fact that these curves, phi and psi, they are continuous. Okay, let's continue. Next, recall that continuous function on a bounded closed region is uniformly continuous. Okay, so that means our function f of x, y is uniformly continuous on D. uniformly continuous on D. Therefore, if delta is sufficiently small, then we have this. If we have the following, if consider 2 points, x and y, and x prime and y prime. If, of course, these are in the region D, for all such points, pair of points, we have if x, the distance between these 2 points are sufficiently close, small, and so that can be also expressed in this way. So this means this and this together means that the distance between these 2 points is small enough. Then this implies the difference between the functional values at these points is small enough. Okay. This can be arbitrarily small. Say epsilon over 3d minus c. By the way, this 3 times d minus c, or these 3's, they are there so that the final result is pretty. So it's not very important, but it's nicer. Anyway, so what we wanted to do was to show that f1, uppercase f1 of x is continuous at x equal to 0, x0. So let's consider this quantity, f1 of x minus f1 of x0. So after some calculation, we will show that this is less than epsilon. Okay. So if we can do that, then we have shown that this function is continuous. Okay. So let's do that. First, f1 of x, and we add and subtract. We subtract and add the same thing. This integral c d f x and y dy plus add the same thing x and y dy, and we subtract another quantity. This time it's x0 and y, and add the same thing to cancel. And the remaining term is negative minus f1 of x0. Okay, so this is just equality. We subtract this, we subtract this and add the same thing. So this will cancel, and subtract and add the same thing. This and this will cancel. So this is same thing. And then use triangle inequality, okay, to split this summation. Okay, so we split this together, and this and this together, and this and this together. So split into three parts. So this is actually less than or equal to f1 x c d y dy. Okay, so this and this, now absolute value, plus and integral c d f x y minus c d f x 0 y dy, here. So another absolute value, and the last term is this one. C d f0 y minus f1 x0. Now, if you remember, this and this, they are where is it? They are here, right? So they are both less than epsilon over 3. And this one, we can combine them together because the range of integration is the same. So that will be f of xy minus f of x0 y. And we have seen this here. Okay, so here x and y and x prime and y can be any points, right? So it can be x, y, and x0 and y. So the same thing. So that is less than this quantity. So we have this is less than epsilon over 3 plus integral. So we move this integral inside. That is first we move this integral inside, and inside that is greater than epsilon over 3 d minus c dy, and epsilon over 3. But this is a constant function here. So this is 3 epsilon over 3 plus epsilon 3 d minus c. So if we integrate a constant function, we have d minus c here. So this will cancel, and we have 3 epsilon over 3, that is epsilon. So therefore, f1 of x is continuous at x equal to x0, and we are done. Okay, now that we have shown f1 of x is continuous in a closed interval, so that this function is integrable. Okay, so this function is integrable over this interval. And we are going to show that this is indeed equal to, so this, by definition of f1, that is, this integral becomes this. Y dx. And we're going to show that this is actually equal to this double integral. Not yet, but next. Okay, now we show that this as a theorem. So this double integral is equal to this iterated integral. So let's show that. First of all, we define a rectangular region that contains the region D. Okay, so region D is something like this. So that is, so this is A, B, and this is psi of x. This is phi of x. Okay, so the region D is this part. And we define a rectangular region that completely contains this region D. So for example, let's consider this rectangle. Let's see, so this rectangle. Okay, so let's say this is D and this is C. Okay, so let's define R as A, B, closed interval, times C and D. And we extend the definition of f of x and y as follows. X tilde, let's define x and y equals to f of x and y if xy is in D, and or it is equal to 0 if xy is not in D. So in this yellow region, the value of f tilde is 0, but in this blue region, or maybe I should say green region, it takes the value of f of x and y. Next, we consider the Riemann sum of this new function f tilde. So for that, we first define a partition of this region R. So we partition this into many rectangular regions like this. Okay, so this will be A is equal to A0, A0 and A1 and so on, and let's say AN, and C is equal to C0, C1, and so on, and D will be equal to Cm. Okay, and we define capital Mij as the supremum of the functional value where x and y is in the subinterval, so Dij. By the way, Dij is the Cartesian product AI plus 1 times Ci and Cj and Cj plus 1. Okay, and also lowercase mij as the infimum of the functional value where x and y is in Dij. Okay, so that means we define capital uppercase Mij and lowercase mij for each of these small rectangles. So by this definition, we have this inequality, trivial inequality. Mij is the infimum of f tilde, and capital Mij is the supremum. And of course, we're assuming x and y, xy is in Dij. Okay. So if we integrate this with respect to y, wait a minute, with respect to y, yeah. Okay. Then, so, okay, just integrate from Cj to Cj plus 1 dy, Cj plus 1 dy, Cj plus 1 dy. Yeah, but this is a constant, and this is a constant, so we have this Cj plus 1 minus Cj less than or equal to this integral less than or equal to this integral. And next we integrate again, but this time with respect to x. So from ai to ai plus 1, so dx ai plus 1 dx. So we integrate this. And of course, this is a constant, and this is a constant. So we have Mij times ai plus 1 minus ai times cj plus 1 minus cj less than or equal to ai plus 1 and cj plus 1 f tilde and less than or equal to capital Mij ai plus 1 minus ai cj plus 1 minus cj. Then we take the summation for all I and j. So let's sum over I and j. And I runs from 0 to n minus 1, and j runs from 0 to n minus 1. And same for this. I and j, and I and j. It's a bit ugly, but let's see. I and j. Okay. Now we are assuming that the function f of x and y is integrable on D because it's a continuous function. And therefore, this sum on the left-hand side, this sum converges to this as we refine the partition indefinitely, this will converge to the integral, double integral, dx dy, and this one also converges to the same double integral. Okay. Therefore, by the squeeze theorem, this one in the middle will also converge to the same value. Okay, so let's write it down by the squeeze theorem. This summation here will converge to from 0 to n minus 0, j from 0 to n minus 1, and integral f tilde dy dx converges to this function, this integral x dy. And also, let's modify this expression a little bit. So we move this summation symbol inside here. And so this is equal to I from 0 to n minus 1, ai plus 1, and summation over j, cj plus 1, okay, this one, we are just so this one is integration from here to here, here to here, here to here, here to here, and so on. So we are just adding them. So after all, what we have is the integration from here to here, right? So, and same for this x direction. So this is equal to actually from a to b, and integration from c to d of f tilde x and y dy and dx. Now, by the definition of f tilde, as when the value of y is out of the region D, the value of this function is 0. So after all, for those non-zero values, this is equal to uh, f, f of x and y. So this should be equal to a, b, and the lower bound, possibly non-zero lower bound is psi of x. And same for this one, phi of x, and f of x and y, dy and dx. And so, after all, this is equal to this, and we are done. Okay, let's see a few examples. Okay, let's consider this integral x plus y dx dy, where d is this region, x and y. X is non-negative and y is non-negative, and x plus y is less than or equal to 2. So we want to integrate this function over this region. So what is this region? Let's visualize this. So here's x, here's y. So x and y, they are both non-negative, so we only consider the first quadrant. Okay, and x plus y less than or equal to 2. So let's draw the line here, x plus 1 equal to 2. It's something like this. Something like this. So this is 2, this is 2. So the y-intercept is 2 and x-intercept is also 2. And so this line is x plus y equal to 2. So less than this means this region. So we integrate this function on this region D. Okay, so let's do it. So first, we consider x as fixed. So let's fix some value of x here. In that case, the range of y is between 0 and something like this. So that is y equals to 2 minus x, right? So y can vary from 0 to 2 minus x. So this integral is equal to, so x varies from 0 to 2, right? 0 to 2. X varies from 0 to 2, so let's write it this way. And y can vary from 0 to 2 minus x. And dy. Okay, dx is already written here. Okay, so first, let's write this way. Okay, so if we integrate this with respect to y, we have y squared over 2, 0 to 2 minus x dx. And, okay, and this is, let's see, x times 2 minus x and 2 minus x squared over 2. And when when y is equal to 0, this is 0, this is 0. So that's it. And dx. And let's see. So we have 2 minus x here, 2 minus x here. Let's factorize it. So 1 over 2, 2 minus x. So this is 2x plus 2 minus x dx. So let's see, 2 minus x, and actually this is 2 plus x. So this is 4 minus x squared dx. And that's 4x minus x cubed over 3, 0, 2, 2. And that is, so when 2, that's 8, and 8 over 3, and minus 0 and 0. So that's this. So 1 over 2, that's 4 and 4. So we have 4 minus 4 over 3, that is 8 over 3. So this is it. And next example, let f of x and y be any function, any continuous function. And we want to integrate, if we want to integrate this function on a region D, where D is defined as this. X is between 0 and 1, and y is between 0 and x squared. Then how can we apply iterated integral for this? So to do this, first we should draw a picture of this region. Okay, so x is between 0 and 1, and y is between 0 and x squared. So x squared is something like this, right? So that is 1. So y is between this and this. So the region D is this region. This is D. So if we fix a value of x somewhere, then y can vary from here to here. And this is y equal to x squared, this curve. So this can be computed as this. X varies from 0 to 1, and then y varies from 0 to x squared. Then calculate this. First integrate over y, then over x. Alternatively, we may consider x as a function of y. Okay? In that case, we can fix the value of y somewhere. Then the value of x can vary from here to here. Okay? Since y is equal to x squared, then x is, so this curve, as a function of y, this can be expressed as x equal to square root of y, right? So the value of x can vary from this value, so that's square root of y, to 1, okay? So alternatively, we can integrate this like this. So from square root of y to 1, f of x, first integrate with respect to x, then integrate with respect to y. We should get the same result. You should try, for example, by substituting f of x and y as the previous example, x plus y, for example. Anyway, so that's all for this video. See you later.